Greetings, ladies and gents, and welcome. In this video, we'll be looking at the final energy extended practice question. Remember that, of course, we are still under our topic, which is the work, energy, and power. So in this case, we have actually covered work, we have covered energy, right? So in this case, we are still in this case on the energy part. So we are doing in this case extended questions on that. So in this case, the only thing that we haven't covered is actually the power. So in this case, what we are going to do is that after this video, that in the next video, what we are going to do would be to look at power, what it is and what it does and why it's important, right? So in this case, if you haven't subscribed, please be sure to subscribe, and also suggest our channel to your classmates, friends, and even your parents, your grandmas, everyone who wants to learn. Okay, anyone can learn these days. So in this case, for question 4, they said that a steel ball of mass 5 kg is connected to a string and swings from rest at point A. They say that as the steel ball swings through the lowest position at point B. Now, in this case, what they are simply implying by that word there, from rest, in this case, they're simply just telling us that in this case, the speed of the object at that point there is simply is 0. Right? So in this case, they say that as the steel ball in this case swings through the lowest position at point B, it collides with a stationary block of mass 2 kg. They say that immediately after the collision, the block moves at a speed of 4.95 to the right on a frictionless track, which is BC. So again, we do not actually have a friction between these 2 points. In this case, you must just keep that in mind as well. So in this case, they said that after the collision, the steel ball and they say the steel ball swings to a maximum height, which is h. So they say that in this case, ignore the effects of friction, assume that no loss of mechanical energy in this case during the collision. So in this case, for 4.1, I don't know why this statement, it kind of feels like the English it went sideways, right? So in this case, for 4.1, they say that what is meant by an isolated system as used in physics. So in this case, an isolated system is a system where there are no external forces such as frictional force, applied force, tension, and in this case air resistance So in this case, so that's for your 4.1. So for 4.2, they say that calculate the velocity of the steel ball immediately after the collision. So in this case, what do we know? So in this case, we know that, of course, at point A, our object in this case is stationary there, but in this case, so they released it. So in this case, when it reached that point there at point B, we do not know that at what speed is that the object traveling. So in this case, they want us to calculate the velocity of the object, in this case immediately after collision. So in this case, we do not know that at what speed was that object traveling before collision, but in this case they are asking us to calculate the velocity of the object in this case after. So in this case, what we are going to do is that we are actually going to calculate this the speed or the velocity of the object before collision, because in this case, if we try to attempt it, in this case to find, of course, the final velocity after the collision immediately, we would not be able to. Why? Because in this case, we don't know that at what speed was the object traveling before, in this case, the collision, right? Immediately before the collision. So in this case, what we are simply going to do would be to calculate the speed of the object, right, at that point B there before the collision. So in this case, what we are simply going to do would be to use our mechanical energy formula, which says that in this case, mechanical energy right at point A simply equal to the mechanical energy at point B. So in this case, if we expand this, will simply be mgh at point A plus, in this case, half multiplied by mass multiplied by the speed squared at point. So that's at point A. All right, equal to mgh point B plus half mass multiplied by the speed squared at point B, which is what we want there. We want to know the speed of the object at point B before the collision, so that in this case we can try to squeeze ourselves and try to find that final velocity of the object, in this case in this case the velocity of the object, in this case after the collision. So in this case what you're simply going to do now would be to substitute our values. But in this case what you must just keep in mind is that these two, all right, they are simply going to give us a bunch of zeros, right? Remember that of course the speed of the object at point A is 0, as in this case. So this simply means that this whole thing here is actually going to give us a 0, right? So in this case for this one, we know that of course when that object is at point B, it is actually on the ground. So in this case our h there will simply be 0, so that would make that whole thing there to be a 0. So in this case what we are going to focus on is simply these 2. So in this case simply be in this, let me just, all right, okay, so let's do this. So simply be in this case mass of the steel ball, which they say that's 5. So be 5 multiplied by 9.8 multiplied by the vertical height at point A, so this will be 1.2. Right, so this is equal to in this case half multiplied by 5 multiplied by v squared at point B there. So in this case what we are going to do there, so if you put this into your calculator, what you're simply going to get would be in this case 80, that's 58.8, so that's 58.8 being equal to, in this case a half of 5, that's 2.5, so that's 2.5, this case of v squared. So in this case we're going to divide by 2.5 on both sides. If you do that, it's simply going to have 23.52 being equals to, in this case v squared. All right, if you take the square root on both sides, what you're simply going to have would be in this case vb being equal to, in this case the speed of the object at point B to be 4 point, and this is 4 point, let me just try to do it this way. All right, yeah, but anyway let me just try to go back a bit. So in this case, so this is the step that we have. So in this case I'm just going to further expand this to be 23.52 being equals to v b squared. So take the square root there. So in this case our velocity or our speed at point B will simply be equal to approximately I think that's 4.97, so on and so forth, meters per second. Remember that we can't round off now. Why? Because in this case this is not actually the final answer. So in this case what I'm simply going to do would be, now if you look at this step, so that simply means that this is my velocity at the point P is simply equal to, in this case 23.52 this. I think I'm just gonna continue to using that one since it's not in this case rounded off. Right, so in this case remember that we are looking so in this case that simply means that in this case the speed of the object at point B before collision is simply 4 point, in this case 84 or 85, if you choose to round that off. But remember we do not round off unless if it's the final, in this case, answer. So in this case what I'm simply going to do to find the final, in this case the velocity of the object immediately after the collision. But remember that of course now we are talking actually about collisions, which actually brings back which actually takes us back to momentum. So in this case what we are simply going to do to find the, remember that they say that assume that in this case assume that no mechanical energy is lost during the collision. So they're actually telling us that in this case we are actually in an isolated system, so there's no energy that is lost. And we know that of course we can also use the mechanical we can also use of course the law of momentum, which says that in this case the momentum before equal to, in this case, to the momentum of the objects, in this case before and after collision. But in this case, if this case there is no energy that is lost. So in this case that's if we are in an isolated system. So in this case they actually gave us a hint there by saying that no energy in this case was lost, in this case during collision. So in this case what we are simply going to do would be to say that the sum, right, of the momentum before collision, so this will be equal to the sum of the momentum, in this case after, in this case, collision. So in this case so remember that we have two objects, object A and so in this case that steel ball there and that block there. So in this case simply be, in this case, a mass multiplied by this case speed initially for, in this case, for, let's say, for the ball, all right, in this case plus mass multiplied by the speed initial of in this case of the box, being equal to in this case mass multiplied by the velocity of the ball, in this case ball, right, in this case after, plus in this case mass multiplied by the velocity of the box. In this case it's actually after after the collision, which is actually the final. So remember that in this case we are trying to look for the final velocity of the steel ball immediately after the collision. So in this case they actually told us the speed of the block immediately after the collision. So they gave us that to be 4.95. So in this case what we are simply going to have to do there would be to substitute in this case our value. So in this case remember that now we are dealing with momentum, so in this case direction is very important there. So in this case what I'm simply going to do would be to take to the right as positive, so simply mean that to the left would be in this case negative. But remember that in this case our system is actually moving to the right. So in this case my mass for the ball, so that's 5. So be 5 multiplied by the velocity initial. So in this case initial so that would be in this case the velocity of the ball before the collision, so which we found that to be in this case 4.8497. but I'm simply going to put this one because these two are equivalent, right? They're the same thing, so this will simply be in this case under the square root 23.52. all right, I'm just avoiding to write all of those decimals there. So this will simply be in this case plus the mass of the block, which is 2. So this will be 2, right, multiplied by in this case the velocity, right, initially, which would be in this case 0, right. We know that of course initially that was actually 0 there, so simply be equal to in this case so this will be the final condition, so which would be mass of the ball, which is still 5, multiplied by the velocity final, which is what we are looking for. So this will simply be in this case plus for the box. So in this case actually we have this is, so in this case for the box we know, so the mass is, so in this case the mass for the box is actually 2. The velocity of the box after collision, they told us that's 4.95. so it's simply be in this case 4.95. so in this case what you're simply going to do there, so if you put this into your calculator, what you're simply going to get is actually 14 root 3. That's root 3 there. So this is simply equal to, in this case now, so in this case this is actually going to give you so that's actually going to give you 9.9. so this is simply be in this case 5 VF plus in this case 9.9. so in this case what I'm simply going to do would be to take this to the other side, so simply be 14 root 3 minus 9.9, so simply equal to 5 VF. So I'm going to divide by both by 5 on both sides, so simply be divided by 5, divided by 5 there, so these two cancel. In this case what I have is my VF simply be in this case, if you put this into your calculator, what you're simply going to get would be in this case 2.87 meters per second. But please note they asked for the velocity. A velocity is actually a vector quantity, so in this case we would need to state the direction, so this will simply be to the right. So that would be to the right, so in this case that would be, just take that down there. So in this case this simply be in this case how you actually obtain that 7 mark there. So in this case what you needed to do was to calculate the speed of the object, or the velocity of the object of that steel ball before collision, and then in this case using the mechanical energy. So in this case after that what you would need to do in this case would be to apply the in this case the principle of momentum, right. So in this case, which would be in this case this what we did, then we would get actually your velocity there, final of that steel block there, since they actually gave us of the steel ball, since they actually gave us in this case the velocity of that box there. So in this case for 4.2.2 they said that in this case calculate height h reached by the steel ball. So they want that that height h there, but remember that we now know the final velocity of that steel ball in this case after after the collision. So in this case we found that to be in this case to be 2.87. so in this case what you so in this case that simply mean that in this case the velocity or the speed for the steel ball at this point here, after the collision, right? So in this case, so still connected there. So in this case, the speed there is simply that 2.87. So remember that in this case, our steel ball is still in this case on the ground, right, in a sense. So in this case, what we are simply going to do there would be, in this case, to calculate the height. So in this case, what I'm simply going to do would be to use the mechanical energy. So I'm going to say that the mechanical energy of the object at this point, it would be in this case equal to the mechanical energy of the object at point E, right? Because they say that in this case we must assume that no mechanical energy in this case is lost. So in this case, what we are simply going to do would be in this case to say that the mechanical energy at point in this case B, which would be let's say E, let's say that's point F after the collision. So this would be in the mechanical energy of the object of the steel ball after the collision, which is which we say that, let's put that to be point F. So simply be equal to the mechanical energy of the object when it reaches that that point, in this case E. So simply be mgh at F plus, in this case, a half mass multiplied by the velocity v squared at point F initially, right? So in this case on the ground. So simply be equal to mass multiplied by the gravitational acceleration multiplied by the vertical height at point E, plus this is a half multiplied by v mass multiplied by v squared at point, in this case E. So in this case, when that steel ball reaches that point H, it will simply have, in this case, a speed of 0 there. So in this case, what we are simply going to do would be to substitute our values. So in this case, again, you notice that this is actually going to give us 0, right? And also this one here. So in this case, remember that when the speed there is 0, that makes this whole thing is 0 there. When height is 0 here at point F, so in this case, this makes everything, so this makes this thing here to be 0 there. So what we are actually left with, simply these two here. So in this case, what we are simply going to do would be half. So let me just put a 0 there, 0 plus half, so that in this case we have mass, which is actually, so they gave us that to be 5. All right, so that's a 5. In this case, multiply, in this case, by the speed of the object before, which is in this case after the collision, which is 2.87 squared, equals to, in this case, 0. So it's, and that's not 0, actually that's mass, which is 5, multiplied by 9.8, multiplied by the height, which is what we are looking for. So in this case, so it will be plus a 0 there. So in this case, if you put this into a calculator, what you're simply going to get is actually 20 point, I'm not going to round that off, so that's 8, that's actually 5, 9.225, and so it's being equal to, in this case, 49. So if you put this into a calculator, you're actually going to get 49. In this case, 8, you divide by, in this case, by 49 on both sides. So what you're simply, so divide by 49, divided by 49. So in this case, your H would simply be equal to, just cancel that, your H will simply be equal to 0.42 meter there. So that will simply be for 4.2.2. So for 4.2.3, they said that calculate, in this case, at the time for the block from the moment it started to move after the collision to in this case and this is to reach point, in this case C, which is 12 meter from point B. So they're telling us that this length here is simply, in this case, 12 meter. Now in this case, what we are simply going to do to calculate that, remember that we cannot use energy principles there. Why? In this case, because we do not actually on our energy principles, we don't have anything that has to do with time there. So in this case, what we are simply what would simply need to do here would be to consult our, in this case, our equations of motion. So in this case, the one that is actually going to work here would be the one that says, in this case, delta x is equal to, in this case, to velocity initial multiplied by, in this case, multiplied by in this case by I think that's delta t, plus a half multiplied by, in this case, by a, the acceleration, multiplied by delta t squared. But remember that in this case, as this object is traveling between point B to C, we don't have actually any force that is actually causing the object to lose its speed. So in this case, that simply means that in this case there is no change in speed of the object. So that simply means that the acceleration is 0. So that would actually make this whole thing here go away. So in this case, as soon as that, so in this case, we know that our A is 0. So in this case, that would actually make this whole thing here to actually be a 0 there. So in this case, what we are left with would be in this case, so I'm actually going to take to the right as positive, to the left as in this case negative. So in this case, remember that in this case our object is moving in that direction. So in this case, what we have would be in this case our displacement there to be 12, equal to in this case of vi, which is that 4.95. So that's 4.95 multiplied by delta t plus a 0. So we divide by 4.5 on both sides. So if you do that, divide by 4.95, divide by 4.95. So those two cancel. So what you have is your delta t, simply 2.42 seconds there. I hope that that makes sense. Of course, I think you can also use other formulas that has to do with time and in this case in the distance, but you must just keep in mind that in this case the acceleration of the object between those 2 points is 0. Of course, there are other formulas. I think I think there's another formula that I've heard other students saying it's a DSTV formula. Yeah, we do a lot of things. We do our gymnastics to try to to retain those formulas there. I don't know what that even stands for, but anyway, in this case, we got our answer there to be 2.42 seconds. So in this case, they gave us another statement. They said this. They said that the block moves from point C with a speed of it should have been actually that should have been there to be in this case 4, that 4.95. Let me just fill that 4.95 in this case meters per second there. So that's meters per second. Let me just write per second. That's per second there. So in this case, they say that my apologies for that. Kind of didn't look extensively on that. So in this case, they say that the block moves from point C with a speed of 4.95, right? In this case, up a rough inclined plane to point D, which is in this case 0.6 meter above the horizontal as shown in the diagram below. Right now, now you might be asking that how did I know that that's 4.95? Remember that in this case they say that in this case there's no friction between point B and C, so that simply means that the speed of the object of that block after collision simply be this, it would have the same speed when it reaches that point C there. Right, do not be shocked. Okay, so for 4.3 they say that state the work energy principle in words. So in this case we know that of course the work energy principle states that in this case it states that the net work done you can say that in this case the work done by the net force in this case is equal to the object's change in kinetic energy. You can actually put it in that way. That's actually the formal definition that they want according to the guideline. So in this case for 4.4 they said that the block reaches point D at that point there with a velocity with a speed of 2 meters per second. So we know that of course at that point D there the object has a speed of 2 meters per second. They said that using energy, I don't know if that's a right one, but anyway, so they say that using energy principles, calculate the work done by friction when the 2 kg block moves from point C to D, right, from this point in this case to D. So in this case we know that of course between these 2 points we have in this case frictional force there, because that's actually a rough surface. They told us there in that statement, in this case in that statement above there, even here they say that the rough inclined plane. So in this case now remember that in this case our object is actually sliding up, right? So in this case as this object is sliding up, the only external force that we actually have in this case acting on that object is actually that is actually the frictional force. In this case they say that using energy principles. Now remember that we have 3 energy principles. Let me just bring those. So in this case these are the energy principles that we have. So in this case remember that this cannot work. Why? Because in this case, let me just take it to that side. Why? Because in this case this only works when we are in an isolated system, when we do not have non-conservative forces. So we know that of course between these points we have a non-conservative force, so we can't use that. So in this case, but what you must just note is that now remember that we're now left with these two. right? So in this case, what are we given and what are we not? So in this case, you notice that in this case, we are not given this length here, point D. We do not know how far this object, in this case, was displaced from, in this case, point C to D. So in this case, remember that, of course, this was simply, so this would actually require us to calculate. So in this case, what you must just keep in mind is that if we decide to use this formula, we are going to sum, in this case, we are going to sum all the work done on the object by all the forces, including the gravitational force. But in this case, if you, in this case, you were to draw a free body diagram of the object as it is sliding up the incline. So in this case, what you must just note is that we would have, in this case, the force of gravity parallel acting downwards. Alright, so that would be Fj parallel. We actually have, would also have, in this case, our frictional force. But in this case, remember to calculate, in this case, our Fj parallel would simply say, in this case, Fj multiplied by sine of theta, and we do not have that angle there. So in this case, this will simply not work. So in this case, the only one that will work would simply be this one. So in this case, how did we also know? They actually gave us that vertical height there. So in this case, we chose to use the one formula that actually best fits the condition that we have, in this case, or what we are given. So in this case, we are given that vertical height. In this case, the only work that the only one that the only energy principle that is actually that would fit here, in this case, that has, in this case, the vertical height, would simply be the non-conservative force. So in this case, what we are simply going to do there would be to say that, in this case, the work done, right, by the non-conservative force is equal to, in this case, to the object. So it's the change in EK plus the change in EP. So in this case, remember that in this is the only non-conservative force that we have between these 2 points is actually the frictional, the work, is actually the frictional force. So that's the only non-conservative force that we have. So it's simply be, in this case, the work done by, in this case, by Fk. So simply be equal to, in this case, half mv squared at point D minus half mv squared at point C plus mgh at point D minus, in this case, mgh at point C. So in this case, what we are simply going to do would be to substitute this. So they're actually asking us to calculate that Fk there. So in this case, what we are simply going to do would be to say half multiplied by the mass of the block, which is 2, multiplied by its speed at point D, which is they gave us to be 2, square that, right? Only square that 2 there, so it's minus half multiplied by the mass, which is 2, multiplied by the speed at point C, which we said that's actually 4.95, so that's 4.95, square that, plus our potential energy at point D, which is, in this case, the mass is 2, multiplied by 9.8, multiplied by, in this case, by the height, which is 0.6. All right, so in this case, this will be minus our mass. Now this simply give us a 0. Why? Because in this case, at that point there, in this case, our object is not elevated any units above the ground. It is actually on the on that horizontal surface there, so it's simply be a 0 there. So if you put that into your calculator, what you're simply going to get would be, in this case, work done by Fk to be, in this case, negative 8.74 joules if you round that as expected. So in this case, this would be the end for this video. So if, of course, you feel like this video helped you at some extent, be sure to leave a like. If you have got any questions, ladies and gentlemen, you are more than welcome to ask in the comment section. Of course, remember that we still have, of course, to do the power part. So in this case, we'll do that in the videos to come. But otherwise, as the story always ends, ladies and gentlemen, this is Sir Mike signing out. Sharp, sharp.